All right, in this supplemental video, we are going to go through a couple of concentration and osmotic pressure calculations to help us figure out molar masses of unknown substances. Now, one of the reasons why this is an important skill is because since osmotic pressure is so easily measured and can give such great results, even with low amounts of substance, this makes a really beneficial kind of result in terms of being able to use low amounts of unknown. And in unknown analysis, this can be really valuable because you may not have a whole lot of unknown to help you figure out what the molar mass of the substance is in the event of other kinds of observational or spectroscopic kinds of analysis being inaccurate or otherwise not usable for the given circumstance. So we've got two examples here. Let's go through each of them in kind. So with example 9 here, we are told we have a 47 milligram sample of a water-soluble non-electrolyte being isolated from a South African tree and dissolved in enough water to make 2.5 milliliters of solution. We determine that the osmotic pressure of the solution is 0.489 atmospheres at 25 degrees Celsius. What is the molar mass of the compound? So from a standpoint of trying to figure out what we need to do, we need to kind of break this down into parts. We have an osmotic pressure. We also have a temperature, and we can use the value of R, which since this is atmospheres, we're going to use the 0.08206 version of that constant. So from this data, we can take our osmotic pressure and determine the molarity of the solution. With the molarity of the solution and its volume, we can turn that into moles of the substance, and molecular weight or molar mass is mass of the substance over moles. So I've got a mass here, I've got moles there. I can figure out the molar mass off of that. So what I need to do is I need to just kind of break this apart into individual steps and solve each of those steps in turn, in kind. So let's go about doing that. Our equation is pi, the osmotic pressure, is equal to I, the Van Hoff coefficient, times m, the molarity, times R, the universal gas constant, times T, the temperature in Kelvin. Now, a lot of those values that we already have. We already have pi, it's been given to us, 0.489 atmospheres. The value of I is 1, because we are told that it's a non-electrolyte solution, which means that every molecule dissolved gives just one molecule in the solution. We don't have any splitting or dissociation going on. We do not know the value of M, that's what we're trying to find. Our value of R, since we are in atmospheres, is going to be 0.08206 liter atmospheres per mole Kelvin. And we are told that we're at 25 Celsius, which would be 298 Kelvin. So solving algebraically for the molarity, 0.489 divided by 0.08206 divided by 298, I get a molarity of three significant figures, 0.0200 molar unknown. So the molarity of my unknown is 0.0200 molar. Again, this isn't surprising because we have a very small amount of sample, and we use this technique in particular for low concentration kinds of substances to give us that information. Now, to turn that molarity into moles, keep in mind that 0.0200 molar is 0.0200 moles of my unknown per liter of solution. So if I multiply this by the liters of solution, which comes from this 2.5 milliliters, 0.00250 liters, point 0.0200 times 0.00250, I get 5.00 times 10 to the negative fifth moles. And so now if I take my molecular weight, it would be 0.047 grams divided by 5.00 times 10 to the negative fifth moles. My molecular weight comes out to be 940 grams per mole. So we can see this particular technique is very effective. We've got a really high molar mass substance, and we are able to determine its impact and its molar mass based on just making a very small sample of it, dissolved in a very small amount of water. So that's example 9. Let's look at example 10. In example 10, we have an aqueous solution made by dissolving 11.9 milligrams of a non-electrolytic protein in enough water to make 4.88 milliliters of solution. If the osmotic pressure is 523 millimeters of mercury for the solution, what is the molar mass of the protein? Same process that we saw in the last example. We're going to go from osmotic pressure to molarity to moles of the protein, and we're going to take the moles of the protein divided into the grams of the protein to figure out its molar mass. So we're not given a temperature here. When we're not given a temperature, it's generally safe to assume that we're talking about 25 degrees Celsius still. That's at least the case for most of the examples that I give. Most books kind of follow that kind of assumption as well. So I've got 523 millimeters of mercury is equal to, again, this is non-electrolytic, so I is equal to 1. Molarity is unknown. R this time would be 62.36 liters times millimeters of mercury over moles times Kelvin, and we're still at 298 Kelvin here. So solving for molarity, 523 divided by 62.36 divided by 298. We get to 3 significant figures, 0.0281 molar unknown. Once again, molarity times volume will give us moles. So I've got 0.0281 moles of protein per liter of solution. And I'm multiplying that by my liters of solution, 0.00488 liters, which would give me 1.37 times 10 to the negative fourth moles. And so my molecular weight would be equal to 0.0119 grams divided by 1.37 times 10 to the negative fourth moles. My molecular weight would be 86.9 grams per mole, which is really, really small for a protein. But nonetheless, this is what the data are telling us. We would probably want to look at this and maybe remeasure some things given what our data are telling us here. But this is how the process generally works, is you make a solution with a small amount of the solid, you determine its osmotic pressure, and then you work backwards from the osmotic pressure to figure out the number of moles, and you compare the moles and the mass to figure out the molar mass. So you won't see this kind of question on the Chapter 11 quiz, but there is a good chance something like that might show up on the exam or on the final exam. So again, just be aware. But that's all I have for this particular video. Thank you for watching, and if you have any questions, feel free to reach out to me and ask. Thank you.